Now let's see how these algorithms actually live in memory. Good news! No new pointer structure appears in this lesson. Each algorithm reuses the adjacency list from the graph representation lesson. It just adds plain arrays, indexed by vertex. Dijkstra stores the best known distance to each vertex. In the array dist of V, it orders its work with a min-heap priority queue that holds a distance and a vertex. Prim stores a key for each vertex. The key is the cheapest edge that can join that vertex to the tree. It also stores a parent and a small flag saying whether the vertex is already in the tree. Prim uses the exact same min-heap as Dijkstra. Kahn's topological sort stores each vertexes in degree, the number of incoming edges. It uses a plain first in, first out queue of the vertices whose in degree is 0. So the pattern is bookkeeping values, one per vertex. Dijkstra and Prim even share the same heap layout. The comparison is flipped so the smallest wins, and the meaning of the number changes. Over the next few slides, we will open each of these arrays and look inside. Let's open that first array and look inside. The array is called dist. It holds one whole number for each vertex. The vertex number is simply the position in the array. In this example, the 5 vertices are named S, T, X, Y, and Z. They sit at positions 0, 1, 2, 3, and 4. This is dist before the loop starts. The source vertex S holds 0 because the distance from S to itself is 0. Every other cell holds infinity, written in F on the slide. Think of infinity as a note to ourselves. It means we have not found any path to that vertex yet. And this is dist after the loop ends. Now every cell holds a real number. The distance to T is 8, to X it is 9, to Y it is 5, to Z it is 7. This second picture is the answer. The whole job of Dijkstra is to turn the first picture into this one. Finding one cell is easy. The address of dist of V is the base address, plus V times 4 bytes. 4 bytes because one int takes 4 bytes. This is the same arithmetic you saw in the arrays lesson. Nothing new here at all. Now the priority queue. It is not a new structure. It is the same binary heap from the heaps lesson. Same layout, same index arithmetic. 2 things changed. The comparison is flipped so the smallest number rises instead of the largest, and a slot no longer holds one int. It holds this small struct called PQ entry. It has 2 fields, a distance and a vertex. 2 ints, so each slot costs 8 bytes instead of 4. This is the real array, captured from a run of the program. Position 0 is the root of the heap. It holds the pair 7. Z7 is the distance, and Z is the vertex. The root always holds the smallest distance in the heap, so Z is the next vertex we will take. There are no pointers anywhere. A slot's children are found by arithmetic. The left child of position I is at 2 times I plus 1. For the root, I is 0, so its left child is at position 1. That is this cell, holding 8T. The right child of position I is at 2 times I plus 2. Again I is 0, so the right child is at position 2. That is this cell, holding 14X. The same rule works further down. Take position 1. 2 times 1 plus 1 is 3. So this cell, holding 10T, is the child of the cell before it. One formula and the whole tree shape falls out of a flat array. One last thing, and it matters. The heap rule is checked on the first number only. 7 is not bigger than 8. 7 is not bigger than 14. 8 is not bigger than 10. The vertex letter is just a passenger. The heap carries it around, but never compares it. Now look at that same array one more time. Something is hiding in it. Count the vertices. The letter T appears twice, once at position 1 and once at position 3. The same vertex is sitting in the heap in two different places. This one is the good copy. It says 8. T at this moment dist of T is also 8. So this entry agrees with what we currently believe about T. This is the copy that will do real work. And this one is dead. It says 10. T, we pushed it earlier when the best route we knew to T still cost 10. Then we found a shorter route and dist of T became 8. But nobody went back to delete this entry. It is still here, taking a real slot in memory. This is on purpose. Removing an old entry from the middle of a heap is slow and fiddly, so we do not. We just push a new copy and we catch the old one later when it is popped. That is the line that says, if D is greater than dist of U, continue. It throws the old copy away without touching anything. But you should see the price. Because we never delete, the heap can grow to the number of edges, not the number of vertices. In this small run, that dead entry sits in memory for 4 more pops before its turn finally comes. Simple code, more memory. That is the trade. Prim uses the very same shapes. We have 5 offices, A to E, at positions 0 to 4. This array is called key. Careful, because key does not mean the same thing as dist. Dist was the length of a whole path from the source. A key is the cost of one single edge, the cheapest edge that can join that office to the tree we are growing. And once an office joins, its key stops changing. It keeps the weight of the edge that brought it in. That is what you are looking at here, the finished state. And this second array is parent. For each office, it remembers which office is on the other end of that cheapest edge. Watch what happens when we read it. The whole tree is going to fall out of this one row of numbers. Start of B, its parent is A, so one edge of our tree joins B and A. Look back at the key array. And that edge costs 2. Next, C, its parent is B, so a second edge joins C and B, and it costs 1. Notice that C could also have joined straight to A for a cost of 3. The array kept the cheaper choice and simply forgot the other one. Now D, its parent, is also B, that is fine. One office can be the parent of several others. This edge joins D and B and costs 4. And last, E, its parent, is D. This edge joins E and D and costs 2. Add the 4 costs. 2 plus 1 plus 4 plus 2 is 9. That is the total weight of the minimum spanning tree. So stop and notice what just happened. In the binary tree lesson, a tree needed real left and right pointers inside each node. Here a whole spanning tree is stored in one plain array of ints, where each slot just names a parent. Position A holds nil, which is -1 in the C code. -1, not null, because these are positions, not pointers. Kahn is the cheapest of the 3. It needs no heap at all. Plain int arrays and 2 moving counters do the whole job. Let's look at 2 of those arrays in the middle of a run with 6 courses. This array is in degree. For each course, it counts how many courses you must still finish before you may take it. 0 means nothing is blocking it anymore. Careful though. Courses 0 and 3 also show 0, but we already took those out earlier. The ready ones are the courses that have just dropped to 0, and those are 1 and 4. Course 2 still waits for 1 more, and course 5 still waits for 2. And this is the queue. It is a plain array. This first slot holds course 0 and it is already done. We took it out earlier, but look closely because the number is still sitting there. Nothing was erased. Instead, we keep a counter called head, and head simply points a little further right each time. Right now head is here at position 2. To take a course out of the queue, we read this slot and move head 1 step right. Nothing shifts, nothing slides left. The other counter is tail, and it points at the first free slot. When a course drops to 0, we write it here and move tail one step right. So head walks right, tail walks right, and they never go back. And now the nice part. Because nothing is ever erased, every course is written into this array exactly once. When the run ends, the queue holds 0, 3, 1, 4, 2, 5. Read that from left to right. That is the topological order itself. The separate order array in the code is just a copy of this one. Let's finish by adding up the memory. V is the number of vertices and E is the number of edges. Every array we just met costs a few bytes per vertex, but the heap is different. The heap is measured in edges. Dijkstra keeps one array, dist. 1 in per vertex is 4 V bytes. Its heap can hold up to E plus 1 entries, and each entry is 8 bytes. So the total is 4V plus 8E. Prim keeps 3 arrays. Key and parent are ints, and in tree is a small flag. Together that is 9 bytes per vertex. Its heap is exactly the same size as Dijkstra's, so Prim costs 9V plus 8E. Kahn keeps in degree the queue, and the order it writes out. 3 ints per vertex, so 12V, and there is no heap at all. That empty box is the reason Kahn is the fast one. And since order just repeats the queue, a version that returns the queue itself would drop to 8V. Now put real numbers in. Imagine a road network with 1 million junctions and 5 million roads. The dist array costs 4 megabytes. The heap costs up to 40 megabytes. So 10 times more memory goes to the scratch work than to the answer. And the reason is the duplicate copies we saw a moment ago. That is the honest price of the simple design.